Lesson 5, Symmetry and Sequences of Transformations. Alright, so basically, symmetry, if you imagine your own body, okay, for most of us anyways, if you split yourself straight down the middle, you would have exactly what you have on the right is the same thing that you have on the left, right? It's an exact image, should be, right? So, if you have thumbs, everybody hold up your hands, okay? Imagine to hold up your hands, okay? Your thumbs are on the same side, right? So if I was to do a reflective image, when they fall through like this, they would line up exactly. Same thing happens if you did your toes. Your big toes are both on the inside, right, Jacob? All right, good. Just want to make sure. I don't want anybody to take off their shoes. I don't want to double check, but. Okay, go ahead. So your big toes are just like your thumbs. They're both on the inside, and then they'll line up toe by toe by toe, right? So that's exactly how a symmetric line is. So if I was going to draw my symmetric line, everybody looking at me, my symmetric line should be right here. Straight through my nose, through my mouth. Okay, everything should split you straight down through the middle. There are very few things inside of your body that are not on both sides. Your heart being one of them. But you have both lungs, right? They're right on both sides. You have 2 kidneys, both sides. Okay. There's a few organs that you don't have 2 of, but for the most part, you are pretty much everything on the left as you are on the right. Okay? Alright, moving on now. So, we're going to re-clarify a few definitions for us. Let's talk about what regular means. Regular polygons, most specific. So, polygon. I want to define poly for you, just to make sure that we know what poly and gon means. Poly basically means many. Okay? So, in other words, I'm going to write many up here. Poly meaning many, and gon, G-O-N, meaning sides. So, polygon means many sides. That's all it is. Okay? Say what? Polygons. Wow, y'all are just crazy kids. Bunch of crazy kids at the game. In a massive outbreak, Elida students yell geometry during a volleyball game and get kicked out. Polygons have gone crazy. Alright, here we go. Regular polygon means all of the sides have equal measure and all of the interior angles are also equal. So this is how I'll write this. You have, they are equal angular, so equa, angular, and equilateral. Equilateral. Okay? Equilateral means all equal sides. If you didn't already know that, I misspelled equal. All equal sides, and equal angular means equal angles. Equal angles. I don't know if I need to specify this, but all equal angles. Okay? So, a regular polygon has equal angles and equal sides. That's all it really means. So when I say regular, that's what I'm talking about. Here's the book's definition just to make sure that you understand everything that I said, and I'll give you another way to look at it. A regular polygon is a polygon with all sides equal in length and all angles equal in measure. If a regular polygon has n sides, just any number of sides, a random number, then it has n lines of symmetry. So if a polygon has 5 sides, then it has 5 lines of symmetry. So let's try to draw. If you want to, you can copy it right out of your iPad. Draw a polygon. Let's just go pentagon because... Okay, I'm going to draw a pentagon from... Nope, just a website. Because the iPad has the internet. I just added the link to the homepage so that you didn't have to type it in. Alright, so we're going to see if we can find the 5 lines of symmetry that are located in this particular regular polygon. They're really easy to find, guys. They're really not as hard as it sounds. I'm going to try to use different colors, though, to make it a little bit more obvious and a little less confusing. Alright, first one. Maybe I shouldn't use yellow. I'll use pink. First one, I'm just going to split it right down the middle like this. Maybe I'll just draw a solid line. Oy. Okay, if I was to take that, fold it in half, it should be the same thing on the right as there is on the left. 1. 2. I'm just going to do it again from the other sides. Each vertex is going to be my next piece. So if I looked at it, boom, there it is. And I'll do the same thing from pretty much every single vertex. Vertex meaning side. So again, fold that one up. We're good there. And so far I have 3. What other color shall I use? Purple, sure. This one right there. And the last one I'll just do with my pencil right there. Okay, so if I draw them all in there, I just count them. 1, 2, 3, 4, and 5. It's simple. Okay, so is a general rule, if you have a regular polygon, okay, if you have any kind of regular polygon, it will match the number of sides as to the number of lines of symmetry. Each one of these lines of symmetry will fold it in half. So let's do a square. Try to make it as square-like as possible. It's as good as my square goes. It's very still rectangular, sorry. This one has how many sides? It's an easy question, guys. How many sides? 4, okay. So how many lines of symmetry should it have? 4. I'm just going to draw 1 to help me with my definition for lines of symmetry. So I'm just going to draw it dotted as if I was cutting this baby in half. Okay, this is my line of symmetry. It's got 2 M's. E-T-R-Y. Line of symmetry. Whoops. Line O symmetry. Line of symmetry. Alright, so all it is just cutting it in half. That's all we're doing. We're trying to reflect it across that line of symmetry. Okay? So I add this little square just to show you what it looks like. Any questions, comments, concerns? Yeah. Did not figure. Alright, so we're moving on down. Okay? A pentagon also has rotational symmetry. A figure that has rotational symmetry will map onto itself more than once every 360 degrees. So remember what 360 degrees does. It does a full circle, right? Yeah. I'm going to see if I can find the shape of the whoa, what is that? Okay. I'm going to do a regular. How many sides does this have? 8. Are you sure? 6 sides. So what is this shape called? Hexagon. Hexagon. I'm just going to trace it real quick. Okay, I'm just going to trace my hexagon as best as I can. This is a regular hexagon. Please excuse me if my drawing skills on this regular hexagon are not beautiful. Okay, so here it is, our regular hexagon. This should have how many lines of symmetry? 6 lines of symmetry, because that's 6 sides, right? I told you it was regular. So, if this thing has rotational symmetry, I'm going to put it down right chair. No. Well, I don't know. It has at least 6. Does that help better? I'm with you. I'm with you.
Because if you split down one side and then on each of the corners.
Right. So maybe we should change our definition to it has at least 6. Does that make sense? Better? So this is what Tegan's telling us. He says you can split it by each vertex and it'll meet with another vertex, but you can also split it straight down the middle of these sides. And that should create more. Now, let's see, there's 6 that if you connect all the sides, and then there'll be 1, 2, 3 more lines of symmetry. So there's 9. Indeed. Okay, so this one might have some more. So what we're talking about now, I was just doing a review right there. What we're talking about now is rotational symmetry, meaning if I put my finger basically right here on the top and I rotated this, when would I get perfectly back in my line? Or will I get perfectly back in my line? Well, I should. Boom. 1 time. How much did you say? Not necessarily 90. Because think about what 90 degrees looks like. Boom. It would have to move at least that much, right? So I think it's a little bit less. I think it's closer to 60 degrees. Okay, that's fine. So if I rotated it again, boom, 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 bam, there it is. And again, I can do it at least 6 times, right? So for rotational symmetry, it shows that I could do this 6 times. So if I rotate this 6 times to go to the exact same spot, okay, so I've rotated it, boom, 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 and I rotated it 6 times back to its original. I've now done this 6 times, and there are how many degrees in a full circle? 360. So how many degrees did I have to rotate it for each one? 360 over 6, which would be 60 degrees. So this object, this hexagon, rotated every 60 degrees will fall back into the exact same shape it was before. Okay, or exact same place it was before. It never changed shape, I guess. Exact same place. So if you want a general formula for this, you'll take 360, divide it by the number of times you can rotate it before you get in a complete circle, and it'll give you the degrees. Okay. So if we did that with a pentagon, okay, and I rotated this, boom, there it is, 1, 2, 3, 4, and it'll do it 5 times. Okay. So if I got it down to 5 times and I knew I rotated it 360 degrees at the end, I would just divide it by 5 and get my answer for 72 degrees in that particular case. Okay. All right. Any questions about that one? Super. Yay? Nay? Okay. Let's move on then. On the second page that we're going to, it says describe 2 ways in which each rectangle graph below could be mapped back onto itself. So in other words, if we're talking about just splitting it, we can just look at a line of symmetry. So I'm going to zoom in on this thing. Boom. Okay, let me see if I can get rid of that glare real quick. Alright, I'm zooming in on this thing. Is there a place where I could just split this baby in half? And it would just fold back onto itself? So he says right on the y-axis. I agree. What about anywhere else? The x-axis as well. It could fold up like hot dog style. Okay? So let's analyze what the question is asking us. Describe 2 ways in which the rectangular graph could be mapped back onto itself. So if you reflect the rectangle over the x-axis, let's talk about a reflection here. If we reflect it over the x-axis, everything that's up here will be reflected down here, and everything that's down here will be reflected up there. Would that give us the exact same image that we started with? Yeah. What about if we reflected across the y-axis? Everything that we have here is now over here, and everything that we have over there is now over here. Is it the exact same? Of course it is, right? What about rotational? Can I rotate this and get the exact same thing? How much do I need to rotate it to get it? 180, so it needs to go around, boom, all the way back. So how many times will this thing rotate before it goes back to the exact same thing it was before? It'll go 360 degrees, but it'll take 2 turns, right? 2 full turns of 180 degrees. So it'll take 1, and then we rotate it again, and it's back on itself, 2. So 2 divided by 360, or sorry, 360 divided by 2 gives you that 180, just in case you already didn't know. Okay, that's really it for that rotational piece. They explain it in step by step if you want to use it. If you want to go look at it. It'll let me flip pages. Alright. Does it not have paper? It's possible. What's it say right there? Transformations in sequence, just meaning move them in order, is basically what transformations in sequence mean. So, let's look at the image that they give us. They give us a figure, a triangle. It's on WVT. Okay, so if we look at WVT, it moves. I'm just going to put this right back there so that you can see it a little bit bigger. If we look at WVT, this is this one right there. It moves across to the next quadrant. What happened to it? And I want you just to focus on one of your vertexes. Okay, so let's look at W. W is now down here. It went from positive 3, 3 to negative 3, 0. Okay, so I'm going to say it went from here to there. How did it get there? So let's think about how it got there. You said it rotated? Okay, maybe. Let's look about where T is. T went from down here to up there. So how much did it rotate if it rotated? They say 180. Okay. I'm not disagreeing with you. I'm just asking questions right now. All right, let's start examining it. So, let's think about where this is in comparison to where it started, right? So if we look at TVW, which is that one on the right, okay, the original, not the image, but the original, you guys say that it was rotated, okay? Where was it rotated from if it was rotated? Was it rotated from the origin? Because if it was rotated from the origin, T would only stay approximately 1 unit away, just a little over a unit away from the origin. So it couldn't be there, right? Say that again. V? You say it was rotated about V? So if it was rotated about V, this would be where it's rotating, then it would just kind of circle around it, right? That doesn't work. Alright, let's just start from the image, okay? So everybody zoom in on that image, the beginning. Zoom in on V, make sure you're able to see the whole thing, so see the whole grid, but zoom in on it so that you're able to follow the directions as I give them to you. Okay? Everybody there? Anybody need more time? Okay. I'm going to get on it there.
Yep.
That'd be wonderful. Thanks. Alright. Alright, the image has a different orientation than the pre-image. We can see that. Examine the shape and placement of them, and it shows that the image appears to be 180 degrees rotated, like you guys just said. So, try rotating TVW by 180 degrees about the origin and comparing it. So, if I rotated it 180 degrees, this is what it would look like. Literally. Okay? Because look at T. Whoops, sorry. Let me move it down just a tad. Look at T. If it was here and it just rotated 180 degrees, it would be right there, right? Because when you rotate something 180 degrees, it goes from whatever it was to the opposite of what it was. So here it's 1, -1, and here it's -1, 1. Okay, so there's T. On W, it was at 3, 3. Over here, W is going to be at -3, 3. Okay, so that's what it looks like if you rotate it 180 degrees. Now, look at what it did when you did rotate it 180 degrees. So we moved it 180 degrees. Here it is. This is that dotted one right there. What had happened from here to where the actual image is? It needs to be translated up. How many units? 3. So I'm not disagreeing with you on the it was rotated 180 degrees, but after it was rotated 180 degrees, it was moved 3 units up. Okay? Alrighty. So, a 180 degree rotation followed by a 3 unit up transfer moves us to the image that was there. So if we move, will not let me move here. Let's see if there's another way possibly to do this. What if we went out of order here and we translated it 3 units up first? So there it goes, boom, 3 units up, and then rotated it 180 degrees. Well, let's look what happens to the image. It goes way down here. And then in order to get back up to where it was, we would have to go 6 units back. So, order matters. So when you are restating it and telling me how you did it, tell me in the proper order. Because if you tell me it's translated 3 units up and rotated 180 degrees, I would do it just like this, and I would be way off. You would have to tell me it's rotated 180 degrees, then translated 3 units up. Okay, order matters. Flip your next page. Let's talk about this one. So if we look at the original image, it says describe a sequence of transformations that could be used to map this trapezoid ABC onto the prime image of it. So it starts here and it ends up there. Okay, this is a lot like Tetris. How am I going to get these two to match up? So pretend this is the hole that you need to get your Tetris block into, and this is your Tetris block. I need to do what with this and what with this?
Rotate it 90 degrees, 270.
Okay, I'm here in rotation, so let's just go with rotation and see what happens. If I rotated this,
90 degrees.
let's say 90 degrees, it's now going to be, look at the sharp end, okay? It's going to be exactly opposite of where it needs to be. If you rotate it 270 degrees, it'll go all the way around and still be pointing the wrong
I
direction.
thought you said you had to go counterclockwise.
Oh, it does. Here's 270 degrees. Ready? I'll do 90 first, and then on my way to 270. So look at specifically A, B, C, D, not the other image.
Wait a second.
So let me rotate it 90.
Wait a second.
Boom, there it is.
Which way did you rotate?
I just rotated about the origin, but this is the shape it's going to maintain. So look at yours. Look at your prime image. Does this look like your prime image? No? Okay, let me rotate it 180 degrees. Does that look like your prime image? 270. Let me move that down so we can actually see it. Does that look like your prime image? No. Okay, so now I'm back to the original. It looks like your prime image here. It just looks completely upside down, doesn't it? So you think we should reflect it maybe? So if I rotated it 270 degrees, like Tegan suggested, and reflected it, let me reflect it for you. You ready? It's getting closer. I wish I could actually reflect it. So, if not on my iPad, but yes. If I flipped it and rotated it, then it would work. Okay? So, we obviously need some kind of reflection here. So, we're going to reflect it and rotate it how many degrees? I'll tell you what it looks like when it's reflected. It looks like this when it's reflected. When your original image is reflected, it looks like this. So if I rotated it 270 degrees, 90, 180, 270, is that the same as your image? Yes. So we're going to reflect it and then rotate it 270 degrees. Let's see. Questions or comments about that one? Might get you a little confused, but be careful. Don't be afraid of just moving things around. Okay. All right.